Good morning, everybody. I hope you all had a pleasant weekend and are ready to start off the week right. Today, we're going to be working a little bit more on mass and energy balances in fluid mechanics, as well as discussing applications with Bernoulli's expression equation. And we may or may not have time to get into momentum. If not, we'll jump in and do macroscopic momentum balances on Thursday. One thing I did want to point out, since we did kind of fall a little bit behind, I went ahead and made the fourth problem on the current upcoming homework set. It should be homework set 3. It's going to be optional as a bonus, as I'm not 100% certain that we'll actually get to discussing that content before the homework is due on Friday. We will get to everything that's needed for problems 1, 2, and 3 before Friday. So if we don't get to it today, we will definitely get to discussing those concepts on Thursday. So with that in mind, let's go ahead and jump in. We can recall from last week that we had derived key information in terms of the mass balances, which resulted in the continuity equation. Or simply for most systems, mass in is going to be mass out, or the density in times the velocity in times the cross-sectional flow area is equal to the density out, the velocity out, and the cross-sectional area out. In developing our description via energy balances, so we have mass balances, energy balances, we arrived at the mechanical energy balance, or the generalized Bernoulli equation, which sums the energies associated with fluid flow in terms of kinetic energy, pressure energy, static energy, work, and friction. Now, if we can assume that work and friction are negligible, we get the simplified Bernoulli expression. Which states that the energy must be conserved and will simply transfer between pressure energy, static energy, and kinetic energy. You can write it like that, or you can write it as how I write it a lot of times. Right, where 2 points of interest are identified. So those are the big takeaways from that discussion. So to get started, I figured we could warm up by looking at this last example problem. that states a pump draws a solution of specific gravity 1.84 from a storage tank through a 3-inch Schedule 40 steel pipe. The velocity of the suction line is 3 feet per second, and the pump discharges through 75 feet of a 2-inch Schedule 40 pipe to an overhead tank with an elevation increase of 50 feet. If this frictional losses through the entire system is 10 foot-pound force per pound and the pump efficiency is 60%, what power is required to drive the pump? I'll give you guys a few seconds to make any big notes that you would like for this before we kind of jump in and start working the problem together. Okay. As always, the first thing I like to do with these types of problems are to draw them. So we've got another supply tank to storage tank problem. And it states that the pump intake and the discharge line are 2 different diameters. One is a 3-inch Schedule 40 pipe, and the discharge, or the second, is a 2-inch Schedule 40 pipe. Now, we didn't really discuss this last week, but I mentioned it in an email to help you guys finish up that homework. But pipe schedule is an important concept as it denotes the expected thickness of the pipe that you were using. And in the book, it should be Appendix 3. It lists dimensions and properties of steel pipe based on stated nominal diameter and schedule. So for example, in the back, if I jump over to that Appendix 3, a 3-inch Schedule 40 pipe is going to have an actual emitter diameter of 3.068 inches, and the cross-sectional area, fortunately, is provided as 0.0513 feet squared. A 2-inch Schedule 40 pipe is going to have an inner diameter of 2.067 inches with a cross-sectional flow area of approximately 0.0233 feet squared. So with that in mind, we can look at this system and start developing our solution. Now, I make assumptions associated with the points I pick. I pick them here, and I assume both tanks are open to the atmosphere. It makes the calculations a little bit easier. And I'm assuming that delta Z is really going to be here to make my points a lot easier. And it said the delta Z in the problem was 50 feet. So one thing I'm going to want to do with this in mind is set up my Bernoulli balance. So I write it. And I recommend every time you do an energy balance, you just go ahead and write it all out. And then ask yourself, what are the things that I can consider negligible? So what values in this energy balance can I neglect for this problem?
Could we neglect change in pressure?
So yes, Claire. Since I said both tanks are open to the atmosphere, and I picked my points appropriately, I can say my delta P will be 0. What else can I neglect in this? Well, I haven't said anything about friction, so I'm going to assume it's negligible. We will definitely talk about friction next week. But for now, we're going to assume the friction is minimal. Oh, actually, I can't. That's already provided in the problem as a set value. Never mind, let me back it up. So the only thing we can neglect in this right now is the pressure. So let's expand this out and see if there are any other terms that we can neglect or not. Well, the other value I can neglect based on how I've drawn it and some of the assumptions I can make is I can assume that U1 is pretty close to 0. The only issue that I have right now is I do not know the velocity of 2. I know the velocity of the intake, which is approximately 3 feet per second. So when the inner diameter is 3.068 inches, the problem states the velocity is 3 feet per second. So in order to find my actual velocity at 0.2 or U2, I have to take that initial velocity, 3 feet per second, and multiply it by a ratio of the diameters, or 0.0513 feet squared divided by 0.0233 feet squared. So if I do that, I should get somewhere in the realm of 6 feet per second, 6.6 feet per second. And now with this, I should have all the values I need to solve for work by just plugging in my values. So U2 squared is 6.26 feet per second squared divided by 2 plus G times delta Z, Z2 minus Z1, or 32.2 feet per second squared times 50 feet, plus work, plus friction, which was given as 10 foot-pound force per pound. So I do that, I should end up with approximately 1,632 feet squared per second squared plus work plus 10 foot-pound force per pound mass equals 0. Now, my friction term and my kinetic energy and static energy term don't have the same units. So I can't do the math yet. What I need to do is divide by G sub C. And I'll go ahead and put it in a different color so you can see that it's going to be a unit conversion. So if I do that, my second squared cancels. One of these feet cancels, and I'm left with foot-pound force per pound mass. So I'm left with approximately 71.8 foot-pound force per pound mass plus work plus 10 foot-pound force per pound mass equals 0. Or my work equals a negative 81.8 foot-pound force per pound mass. So that's my work. Now I just need to come up with our power. Well, our power is our mass flow rate times our work over our efficiency. And our mass flow rate is simply our density times the velocity times an area times work over efficiency. So our density was 1.84 times water, 62.4, our standard pound mass per cubic foot. Our velocity, I'm just going to use the 3 feet per second times its area, 513 feet squared. The work we've identified was 81.8 foot-pound force per pound mass divided by the efficiency, which was 60% or 0.6. I do a units check. So the pound mass goes away. The cubic feet goes away here. So I'm left with foot-pounds per second, which to get that into horsepower, I just have to divide everything by 550. And this will leave me with horsepower. So I do this math. I get approximately 4.4 horsepower.
I have a question.
Yes.
Did you take the absolute value of your work?
Yes. Yeah, that was something I touched based on last week. For the energy balance, the work will be negative if done on the system. However, when I'm calculating my power values, I don't care about the sign because at the end of the day, I'm going to need that in terms of an actual value, right? So, you know, you can put it as a negative horsepower, that's not going to tell you anything.
Thank you.
Oh, you're fine. Any other questions that I can clarify for this example problem? If not, I'd like to switch gears and start talking about some specific applications of Bernoulli's expression or Bernoulli's equation. And so the first application we're going to talk about is tank draining. So if I have a tank, and at the bottom of this tank is a discharge, and it's filled with everyone's favorite water. I set this z equal to 0, this equal to some height h. And I want to know what is the velocity of the water leaving through the bottom of the tank. Well, the first thing I would probably do is pick some points. So I'd probably pick the top of the tank, and I'll pick the outlet right here. And let's look at a simplified Bernoulli balance. So I'm going to have U1 squared over 2, P1 over rho, plus G times Z1 equals U2 squared over 2, plus P2 over rho, plus G times Z2. So my question for you all are, what values can I neglect in my Bernoulli balance?
You can
Which-
assume atmospheric pressure at points 1 and 2, so you can get rid of the pressure terms.
Okay, so I can say P1 is approximately atmosphere, P2 is approximately atmosphere, such that if I do the math, these terms cancel each other out. I like it. What other values can I neglect?
Can you assume that the velocity at 1 is negligible compared to 2?
Yes, I can. I can say U1 is negligible. Anything else? Or is that it?
Could we say that Z2 is 0 since it says so in the diagram?
That you can. So, to solve for that velocity, I have an expression that says U2 squared over 2 is equal to G times Z1. Or U2 is equal to the square root of 2 times gravity times Z1, which in this case is the height. So I don't need anything in terms of fluid density or any sort of properties. I just need to know what's gravity and how much fluid is on top of that outlet to estimate that velocity as it leaves the tank. Now, one thing we'll find is that the actual velocity differs than what is estimated by this Bernoulli balance. And it's a result of what happens to the fluid as it flows out of the system. So if I zoomed in that exit or orifice, Bernoulli assumes that the flow velocity is going to look a little like this, such that the flow area leaving is nearly identical to what we see in terms of the actual dimensions of the orifice. However, in actuality, the fluid momentum causes a contraction effect as the fluid leaves the tank, such that the actual flow area has a minimum flow or a contraction flow area, or contracted flow area, excuse me, as compared to the actual dimensions of the outlet itself. And so this discrepancy results in what we call a contraction or discharge coefficient. And so if we were going to look for the more corrected form, we would have an expression that looks like this, where CD is our discharge coefficient. It has a lot of names. I'm going to call it discharge coefficient. It's also called the coefficient of contraction. And this little smaller area is called the Vena Contracta. It just states that the flow doesn't occupy the entire outlet in most systems. And the actual discharge coefficient can vary somewhere typically between 6 and 1.6 and 1. And it's largely a function of the geometry of the outlet itself. Things like what's considered sharp-edged orifices have low coefficients of contraction, and well-rounded orifices have high values of discharge coefficients. So let's take a look at an example together. So let's say a completely filled 10-foot water tank, 30 feet in diameter, has a 4-inch outlet at the bottom. Why it's so small, I'm not sure. If the outlet is sheared off, what would be the initial flow rate of the water? And how long would it take to drain the water? Assuming the discharge coefficient is 0.7. So let's look at our example. We got a big tank of water with the height is 10 feet. The diameter is 30 feet. The outlet is 4 inches in diameter. It's filled with water.
Hey, Dr. Lopez, we can't see your drawing.
Thank you. I'll switch it back. I know you guys are eagerly awaiting each day's new artistic rendition of the world around us. So the question is, what is the initial velocity of the water? I actually also said the flow rate too. And when I say flow rate, a lot of times I just mean volumetric flow rate. And so we'll just look at volumetric flow rate. So based on the expression we developed, U2 is equal to the discharge times 2 times gravity times height. Discharge coefficient is 0.7. Gravity is the same, I hope. And height is simply 10 feet. So if I'm going to solve for the velocity, I would simply say U2 is equal to 0.7 times the square root of 2 times gravity, 32.2, feet per second squared times height, which is 10 feet. And that leaves me with a solution of approximately, I got about 17.8 feet per second, which is quite a bit. So, and now if I wanted to find flow rate, my flow rate is simply my velocity times my flow area, which implies that if I'm going to use the same expression, I would have an expression that looks like this for my flow area. Or my flow rate is simply my 17.8 feet per second times my cross-sectional flow area, which in this case would be pi times 4 over 12 feet squared over 4. Or about 1.55 cubic feet per second, which would be, if I wanted it in gallons per minute, it would be pretty high. So I'm not going to put it in gallons per minute. That's a lot of flow.
I have a question.
Yes. Yes, sir.
You gave 2 diameters in this problem. So I was thinking how we did before, how we set up a ratio between the diameters to find the velocity. But that's not the case here.
No. When we're looking at that, if I was going to do the Bernoulli just how I did before up here, I would end up with the same exact expression, where U2 is equal to the square root of 2GH. The only difference is, and now I'm inputting my contraction or discharge coefficient. And since my fluid is flowing out of that orifice, that's the cross-sectional area I need to find my flow rate.
Okay.
So now the tricky part is part 2 of this question that states, how long would it take to drain the water? Well, what's going to happen to the velocity and the flow rate as the fluid leaves the tank?
As the fluid leaves the tank, the velocity is going to decrease because the height is decreasing.
You are correct. And so, yeah, the velocity is going to fall because as the fluid leaves, there's less water in the tank. And so the static pressure, which by Bernoulli's is what's happening here, right? We're converting potential energy caused by that static potential energy, and we're converting it to kinetic energy. So as the water leaves, there's less potential energy, which means there's less energy to be converted into kinetic energy. And so that's going to result in the velocity decreasing as well as the flow rate decreasing. That means if we want to figure out the time necessary to drain the tank, we have to look at this problem in a different manner, right? We have the same situation, but now what we have to think about is if I was going to draw a system, and my system being the water in the tank, or the tank itself, however you want to think about it. how could I write a mass balance for this? Keeping in mind, if we went back to 307, we would have mass in minus mass out plus mass generated minus mass consumed equals mass accumulated. So instead of me just answering it and fishing for it, I want you to, I'm going to shoot you all in breakouts here in a second, but I want you to figure out how can we simplify this mass balance, as well as with the terms that remain, how can we define each term such that we end up with a function of height of the tank versus time. So when you think about that for a few seconds, and then I will shoot you all off into breakout rooms so you can think about it, talk about it for a few minutes in groups, and then we'll come and talk about it as a class. My way of breaking up today's lecture a little bit. All right. Feel free to go. Well, we'll touch base in a few minutes and talk about it again. All right. All right. How did it go? Okay. So what have you guys been able to develop for this one? Let's start with the mass balance. Which terms can I safely neglect?
You can neglect mass generated and mass consumed.
Okay. I don't see any reactions. Is that it?
And could you neglect mass in since that's not changing?
I could neglect mass in because there's no water coming into the tank. So what I'm left with is mass out equals mass accumulated, or I would probably write it as mass out equals negative mass accumulated because it shows that there's negative accumulation in my tank. So I need an expression that describes the mass flowing out of my tank. So what did you guys have in mind for that expression?
Would you use the continuity equation?
I could. I would, to a certain extent, yes. So if you were to use the continuity expression, what would you get for mass out? Well, I could state that it's the density out times the area out times the velocity out, right? And I already have an expression for the velocity out. So I can say density times my area out times C sub D square root of 2 GH. So now I have to figure out, well, what's my expression for my mass accumulation? So how can I quantify the mass or the negative accumulation of mass in my tank? Well, my density is going to be involved. So if I have density times the negative volume of fluid in my tank, I can ask myself, well, how do I solve for volume in my tank? Well, I'm going to have the area of fluid in my tank times the velocity of fluid in the tank. Now, my fluid in my tank isn't necessarily going to have velocity, but how can I quantify my loss of fluid in my tank? Well, I can quantify it by saying it's the change in height and with the fluid in my tank with respect to time, right? Which means my mass accumulated is equal to negative rho area of the tank times the change in height with respect to time. So if I can combine these two expressions, what I'm left with, which I'm going to tweak here for a little bit, and I can say, well, my densities cancel because the density of water leaving the tank is the same density of the water in the tank. So I'm left with a negative change in height with respect to time times the area of my tank equals the area of the outlet or the exit orifice times my discharge coefficient times 2 times gravity times height. So I do a little rearranging of this expression, and I am left with the negative height over the square root of height equals area of the orifice over the area of the tank times my discharge coefficient times the square root of 2 times gravity times dt. So if I integrate this from my initial height to my final height, and I integrate this from 0 to t, I'll have an expression that states my height as a function of time. So if I do the integration of essentially the square root of h, I should be left with what? Square root of h times 1/2, I believe, from initial to final equals, and the negative still there, area out, area of the tank, discharge to g, and then that's just time evaluated from 0 to t. Which means if I plug this in, I should be left with h final minus h initial times negative over 2, which is just the 1/2, equals area out, area of tank, discharge coefficient times 2g times simply t, because it's going from 0 to t. So if I distribute the negative, I actually end up with h initial minus h final over 2 is equal to area out, area of the tank times discharge times square root of 2gh. Oh, you're right, I did forget the square root. And if I rearrange this to solve for t, I should be left with all right. Double check my notes because I don't believe my solution here. My discharge coefficient ends up on the bottom. I end up with like a square root of 2g on the bottom as well. Times, yeah, that should be about it. One thing I'm not certain about is this 2. This 2 doesn't seem to be in the right place. Just double checking this because it doesn't seem right. The 2 should have ended up on the top because it was on the fraction. A -2. That makes more sense. This is why you always double check the math. So you end up with a lot of radicals, unfortunately. So T should be area of the tank over the area of the outlet times the square root of 2 over G times discharge coefficient, which I'll put over here to get it away from the radicals, times the radical of H initial minus H final. So what looked sort of simple ended up a lot more complicated. Any
Dr.
questions
Lopez?
on that? I know I had to make that quick correction on that too.
Dr. Lopez, I do have a question.
Go ahead, Harrison.
How do the heights both fall under the same radical when you integrate?
Actually, they shouldn't. You are correct. Thank you for that. It's one of those derivations that you end up with so many of these that gets a little messy. So with this in mind, one other correction you can make, since the area of the tank and the area of the orifice both have a pi d squared over 4 design, you can really state it's the diameter of the tank squared over the discharge coefficient times the diameter of the orifice squared. And that way you don't have to worry about pi and all those things. So if you were going to solve for the time it took to drain this tank, now that we have this expression developed, it simply requires plugging in the values. So the tank diameter was 30 feet squared. The discharge coefficient was 0.7. The orifice diameter was much smaller, 4 inches. Square root of 2 over gravity, 32.2 feet per second squared. My initial height was 10 feet, and my final height was 0. And so I'm left with an expression that looks like this. So as you can imagine, you end up with quite a lot of time. So doing this really quick. I get about 9,109 seconds, or approximately 2.5 hours to drain the tank. And that accounts for that change in velocity and flow rate at the discharge as a function of the static potential energy changing because there's just less water in the tank over time. Any other questions on that application and example associated with tank draining and how we can apply Bernoulli's equation? So if not, I'd like to move on to the next application I want to talk about, which is Pitot tubes. And so Pitot tubes are kind of an interesting way to look at various things associated with a flow system. Now, if I've got fluid moving through a pipe, and I ended up with a couple things. One would be just, kind of an extension of the pipe. Let's say it looks like this, and this is kind of glass and see-through. And then I had another type of extension, but instead, this pipe extended into the flow area. What I would find is that each of these would have some fluid within them. But the question would be, what information am I gaining by looking at the relative height that I see off of these pipes? Well, I can do a couple things. Let's look at the tip of these. These systems as a function of the beginning or the entrances of them. So if I was going to look at this first tube, I can see some interesting things. Now, first thing, I'm going to assume both this is atmospheric and this is atmospheric, such that I can just make this a little easier and say this is 0 gauge. Now the velocity at the top of that tube is going to be 0. The height as compared of Z1 and Z2 is just going to be H1. And U2 is going to be at the exit, since it's just kind of sticking out. So the velocity there is going to be fairly negligible, right? Because I'm looking really close to that wall. So I'm going to say this is negligible. So what this tells me is that the height I'm seeing off of that first tube is simply a measure of the pressure energy in my fluid system. If I'm looking at the second system, so this was the first tube. If I'm going to look at the second tube, I can do that same analysis, looking at U2 versus U1. I forgot the squares here, I apologize. And I'm going to say, okay, my velocity at 1 is negligible. P1 is atmospheric or 0 gauge. My Z2 and Z1 is going to be some height. I'm just calling it H2. Not really super concerned about the actual height that it is. But the entrance now is within the flow field, so I expect that fluid right there to have some velocity. And so now that height is measuring both the pressure energy of the system. I shouldn't have said H2. That makes it, oh. As well as the kinetic energy of the system. So looking at just this short tube, I'm measuring simply the pressure energy and looking at this second tube that goes within the flow field, I'm measuring both the pressure and the kinetic energy. So by having both tubes present within a flow system, I can not only measure the pressure within my flow system, but I can also determine the velocity of the fluid as it moves in the system. And so Pitot tubes are a way of measuring, let me change my, both static and dynamic energies associated with fluid flow. And what that really means is you're measuring kind of the pressure energy and the kinetic energy. Now, as neat as this is, modern design of Pitot tubes use a much more sophisticated way to measure these forces. And so instead of talking about them a lot, I figured I'd just kind of show you a little video that discusses how a more updated system works. Granted, my video may not work. So give me 2 seconds to pull it up. My hyperlink seems to be dead. Okay. All right, so hopefully you can see my wonderful YouTube now. So I'm gonna just stop talking and play this, and you can kind of see how they're using a really sensitive pressurized membrane to record and transmit flow parameters using this really sophisticated differential pressure Pitot tube. Can you guys not hear the sound?
I can't hear anything.
That's unusual. Can anybody else hear it, or is it muted? If I play it again. Can you hear, yes or no?
No.
Okay, well then I'll just send an updated link. Thank you. Then I'll just kind of describe really quickly. So the way this updated pressure Pitot tube works is you've got essentially a rod that's in the flow area. It's open at various points, so you kind of get an average of the flow, which is what we usually rely on, that, you know, that mean average of velocity. And then essentially a diaphragm. Then as flow occurs, the essentially energy or force exerted on that transducer will show a differential between both sections. So if you have flow coming in, that diaphragm will be deflected as a result of essentially the kinetic energy hitting that side of the pitot tube. And that difference is going to be measured by that diaphragm and transmitted to the metering device. And the degree of deflection is correlated with the flow velocity. The beauty of this design is that if the flow is reversed from any point, that deflection will also be reversed. And so this presents a really elegant way of designing a pitot tube to not only get a good representation of your flow field, but also being able to record both forward and reverse flow. Like I said, I'll send an updated link. I apologize for the lack of sound. All right. Last thing for today, let's look at an example, which is calculating the velocity of water flowing through a pipe if my simple pitot tube is installed and shows a height of 2 feet, with a secondary static tube installed showing a height of 8 inches. So I'm going to go ahead and let you guys work this together in breakouts. So go ahead and spend the next 3-4 minutes doing this calculation, determining the velocity, and then I'll see how well you all did in a moment. All right, they should be open now. I mixed it up a little bit. So go ahead and do that calculation. The static tube has a height of 8 inches. The full-on pitot tube has a height expression of 2 feet. How's the lab going, Elahe?
Trying to do some tubing right now at the very moment.
Where are your glasses?
Meeting. I'm honestly not doing anything. This is what I'm doing. Trying to connect this to the water. No chemicals are around.
Okay, I'm taking a screenshot.
No.
Too late.
I have a meeting I'm talking to. Oh yeah, sorry. The other person in the lab is like, are you talking to me? I have everything.
You need your glasses.
Okay,
Yeah, but if somebody comes by with a chemical and splashes you.
Splash.
Are you guys doing communal lab glasses still, or have you assigned your own
No,
glasses?
this is mine.
Okay.
Yeah.
I think one of the things I'm going to have to get rid of because of COVID is
Yesterday
sharing
we were
of glasses.
talking with Hanif about like emailing you and Dr. Prager about assigning a day for all the grad students to come so we can clean 221.
Yeah, a couple years ago I had planned essentially each semester having a cleanup day at the end.
Yeah, so like we are committed to doing it. I even mentioned it to Dr. Smith that I would do it, honestly, because it's messing with my OCD.
The problem is we can't have every graduate student being in the same place at the same time. I guess technically,
like,
if you guys are comfortable with that, go for it, but
yeah. It's just that honestly we can't find anything, and Hanif was saying that we should wash the lab coats. I was like, we should throw away the lab coats. We're not washing those. We're throwing them away.
They should be replaced about every 2 years at least.
No, anyways, right now because of Corona, everyone should have their own lab coat.
Well, that should be a given.
Yeah, but it's not a given. Just saying.
Yeah, we're gonna talk about lab safety this week in our faculty meeting.
But that lab like needs cleaning very badly. I'm gonna stop my video.
Are you there, Lahe? If I share this really quick with you and I play this, can you hear it?
Okay. No. Are you sharing? Okay, so are you sharing like at the bottom of the screen? You can choose what you're sharing. You have to put it on computer. Right now it's on your headset. Do you get what I'm saying?
Oh, yeah. So I have to share my screen and share computer sound. There, I
Yes.
see. So now can you hear it?
One principle is flow
Yep.
management based on dynamic pressure.
Woo! Thank you for helping me do that. I knew it
You're
was a
welcome.
simple thing I was forgetting.
Yeah, this Zoom has so many.
No, I
funny
appreciate that. Now I
You're
can share
welcome.
the video and everyone can have our video time. Thank you for putting on glasses.
You're welcome. It's just like when I like breathe because of the mask, I can't see anything.
Welcome back, everybody. All right. Well, how did it go? Jacob's over there in Endgame.
Yes.
What did you all get for your velocity? Did we get a value? Or do I need to put this on the midterm?
I got 1.63 feet per second, but the units are really weird in these equations whenever you try to add them together. So I'm not sure if that's right.
Yeah, I got tripped up on the unit as well.
All right, really quickly, at the solution. Since we're concerned about the difference in the heights, and trying to determine that velocity, the static showed a height of 8 inches. The static and dynamic showed a height of 2 feet. That means if this is a function of pressure, and this is a function of pressure, a function of terrible handwriting, and the kinetic energy, to find just the kinetic energy, you just find the difference. And so the difference, H2 minus H1, is essentially 8 inches minus 2 feet, or simply 24 inches minus 8 inches, which is 16 inches. And so once you have that to find the velocity, it's just the square root of 2g delta h, or the square root of 2 times 32.2 feet per second squared times 16 over 12 feet. So you do that, you should get a velocity of approximately 9.3 feet per second. And so you could come to that same conclusion doing all the balances, but just applying the principle, noting that the static tube's going to show you height as a function of pressure energy. The second Pitot tube is going to show you both pressure energy represented as well as kinetic. So the difference just simply tells you what the kinetic energy will be. All right, guys, we're over time. So I'm gonna let you go. One thing I do want to note is I unfortunately have a meeting today at 11, so I will not be able to hold office hours right after class. I will hold office hours this afternoon at 1. So if you have questions, feel free to come by. And also, good news is Elahe showed me how to fix my sound. So if you want to stick around for a few seconds, you can see the wonderful.
Here is how this measurement method works.
But if not, you're free to go.
Pitot tubes have a rod-shaped measuring element that is inserted into the pipeline perpendicular to the flow direction. On the front and rear of this probe are several holes. 2 separate tubes connect these holes to a differential pressure sensor. With its 2 pressure chambers, separated by a diaphragm, the tiniest pressure differences in the flowing fluid can be precisely measured. The individual pressure taps are distributed along the entire pipe cross-section to ensure a representative measurement. If there is strong interference in the flow profiles, it's advisable to fit a second Pitot tube, rotated by 90 degrees. If the fluid is not flowing, the pressure before and after the probe is essentially the same. As soon as the fluid starts to flow, an additional impact pressure against the front of the probe is generated, also known as the dynamic pressure. On the rear of the probe, in contrast, only the static pressure, which is not related to the flow, is still measured. As a result, different values are detected in the pressure chambers of the sensor. Higher pressure against the flow and constant pressure on the rear of the Pitot tube. This pressure difference is a direct measure for the flow velocity and thus the mass and volume flow in the pipe. The higher the flow velocity and therefore the dynamic pressure, the greater the differential pressure measured. Pitot tubes are able to register the flow in both flow directions. This means that balancing measurements, for example in gas pipeline networks, can be carried out at any time.
So there you go. Good little illustration of how that works. Thank you guys for coming. I appreciate you all, and I hope you guys all have a great day.